I studied the synthetic pathways for sitagliptin. I think I figured out how to pronounce it, but Januvia is easier, so I'm just going to say that. So, yeah. Okay. So sitagliptin is an anti-diabetic drug, so it's used to lower blood sugar in patients who have high blood sugar, so mainly people who have diabetes. So this is um, like just what it looks like as a drug, and this is the structure of it. So this is the important part of the structure that the synthetic pathways focus on, is this R-configured amine attachment. So these are the two pathways. This is the chemocatalytic pathway and the biocatalytic pathway. So chemocatalytic is just like organic syntheses of the pathways. And the percent EE was really impressive for both of these. So this was 97% for the chemocatalytic, and like we studied in DJ's class, percent EE is just the level of enrichment of one enantiomer over the other. So 0% would be like equal parts or racemic mixture of two enantiomers, and closer to 100 is going to be enantioselectivity of one enantiomer over another. So this was really impressive for the chemocatalytic reaction, but it was definitely more impressive for the biocatalytic reaction. 99.95% EE, so it's probably like 100% EE, but you have to like leave room for just a little bit of error, so they kind of rounded down just a little bit. It's kind of like in hand sanitizer, we have kills 99.9% of germs. You have to leave room for that 0.1%.
Yeah, the one tough one. Yeah.
Yeah, just that one tough germ.
Yep.
So again, so the EE was just really impressive and really reinforced like enantioselectivity for that R configuration amine at the end. And here, this was a asymmetric hydrogenation step in the chemocatalytic pathway. So this was similar to Beth's L-DOPA synthesis. So here, the hydrogenation is just saying that it's asymmetric because the hydrogenation didn't approach the same face of the compound equally, which is why we have this high percent EE. It approached one face more than the other. So, and then this Josephos here is probably just a chiral ligand attached to the rhodium that just, again, reinforces enantioselectivity. So it's just a lot of like one enantiomer over another. It's the main part of these steps. Okay, and then this is the biocatalytic approach. So transaminase and PLP were important steps in getting this selectivity of the R configuration over the S. So PLP is pyridoxal phosphate, and it can do a lot of reactions as a cofactor, but it mainly focuses on transamination. So this is the structure of PLP. And then this, I found this online, which was the racemization mechanism.
Oh, yeah. Okay.
Or how PLP is used. So this is the PLP. Is this like connect? Like this idea?
Well, this is unfortunately, I think, one of the, well, let me see here. What's going on? Let's see.
It's like converting an enantiomerically pure mixture into a mixture where one of the enantiomers is more than the other. So that's what like these mechanisms are showing.
Oh,
it's just using
yeah.
hydrogens from different amino acids.
Yeah, yeah. So this is a little bit different than PLP being used as a transamination catalyst.
Oh, okay.
Yeah, the one thing that is true, the common between what you're showing and what it does in the transamination is that the PLP makes an imine with an incoming nitrogen. So like in your reaction, that would be the isopropylamine. So this has some commonality, but not total commonality with the transamination reaction.
Okay. Okay, so we're just going to skip this slide then. So pretend I didn't show you that. But yeah, so this is how transaminase works in the biocatalytic pathway here. So transaminase has a limited substrate range, which isn't always good because it means that the enzyme does a specific reaction on very specific substrates that occur naturally. So researchers have to implicate mutations in the enzyme to make it able to react with the substrate that they want. That's what was happening here, was they didn't have an enzyme yet that could like nicely produce Januvia. So they started with base enzymes and were able to make make a final enzyme that could make Januvia in like a good industrial way. So transamination is a common reaction, and in this case they had to it causes mutations in the enzyme to interact with Januvia, like I just said. But just because it's common doesn't mean it can be applied easily, because again, you need that specific enzyme substrate application. And this is how transaminase works, but another way of understanding it is like this. So this is just like simplified more. So transaminase, the name, the trans part of it doesn't apply to stereochem. It's more like replacement almost. So if you think of like an ester, and how if you add more alcohol to an ester, that new alcohol is going to replace the original alcohol that was attached. So that's kind of what's happening here. You're replacing this with the new amine here. So isopropylamine was probably pretty good to use because it produced acetone in the end, which could be reused and recycled for different purposes, and was able to like get the job done properly. That's all of this. So this was the mutations they applied to a starting enzyme to make an enzyme that would, again, desirably be able to make Januvia. So they started with this base model enzyme called ATA117, and at each, they had like several rounds. So each one of these horizontal lines is a round, and these are all the mutations that they added after each round. And the improvement over parent is saying like, what was the improvement from this step to this step? So here we find like really good improvements at the fourth round. So in this round, it reacted on substrate 2, and substrate 2 is that prostagliptin methyl ketone, and that's where you wanted to see the change on the amine. And so this was the first time it reacted with that ideal part of the substrate, but this is where it was actually active for the first time. So it really took 8 mutations to finally see some changes. Then after that, they were able to make improvements based on different standards. So it might be according to assay or how much substrate they added of like organic solvent to the water. So there's a lot of different things that they measured throughout the process of creating the best enzymes.
Can I jump in here real quick, Emily?
Yes, please.
So I just want people to sort of recognize what a little bit of this nomenclature is. Can you just explain like what G136Y, for example, like what does that mean?
Yeah, so that's saying that in the amino acid chain at spot 136, the glycine was changed to a tyrosine, and that's what each of these imply. So just like the first amino acid, the spot, and then the amino acid that was replaced.
Yeah, so that's what people mean when they say mutation, is that you're changing one amino acid to a different amino acid, and then that can then have consequences for the function of the protein. In this case, its function as a catalyst.
Mm-hmm. This is kind of a silly question, but
there are no silly questions in my opinion.
Okay. But are the mutations additive? So like if you're the one you have in a box round 4, does it mean it has all of the mutations prior to it as well as the ones indicated?
Yeah, so at the very end, when they finally got a desirable enzyme, it took all of these, like probably 50 or so mutations to get there.
Cool.
But yeah, what I learned, Oh, go
Yeah,
ahead.
each round is on top of the existing mutation. Yeah.
And then once you have the gene, like you theoretically kind of have it forever, because now you have like the pattern for it and everything.
Emily, I just have a quick question. So
Yeah.
what are the numbers on like under the improvement over parent? Like, do you know what those mean or no?
I don't know like the units on them.
Mhm.
I think it's just some sort of like unitless factor. Oh, it has to do with like 75 fold. That's what it is. So like here, like this line, this round improved 75 fold from the previous line, and this improved 9 fold from
Oh,
this round. That's what those are.
okay.
Yeah, so it was like really impressive here, and then like it was positive improvements, but just like in lower uh, acceleration rates. Yes. Is that a good way of saying it, Scott?
I think so, yes. And the weird thing about this table is that, so just sort of reading it from right to left, it's like here are the new amino acid substitutions or mutations, and then the next couple columns are the new condition that they are subjecting the mutant to. So it can be a change in the amount of substrate, so like, which is the ketone that they're trying to do the transamination reaction on. It can be a change in what the reaction conditions are, or the assay changes, which would be starting to add some organic solvent to the aqueous buffer that they're doing the reaction in. So it's the full, so then the improvement over parent is how much better is the enzyme under these new conditions than the previous one or its parent. So they're sort of optimizing for a couple of different things. One is just to be a better and better catalyst, and then but also to be able to tolerate the presence of some organic solvents, which proteins oftentimes can't do on their own, and also to be able to just dissolve a lot of the reactant ketone in the reaction mixture. So you can see they're getting up to 100 grams per liter of the Januvia ketone sort of by the end, whereas in the beginning it was only 2 grams per liter. So they're trying to just make the whole thing very, very concentrated. So it's a lot. This table summarizes probably dozens of people years of work, I think. Yeah.
Like just a collection of a lot of different data along the same lines, kind of.
Yeah, because they're also not describing the mutants that were either worse than the parent or were no different, right? So a lot of stuff that they almost certainly did is not on this table. Maybe most of it is not on this table. Yeah.
Right. So kind of moving away from the table, the protein's also a dimer. So this is just kind of visually showing the mutations that were made. So RD is just round. So after the first round, you can see here in the purple, this was the G136Y mutation. And it's just showing like where it was. So also a dimer is 2 copies of the protein, and they're just bound to each other in the same way. So like these are both the same, they have the same makeup, but they're just independent but bound to one another. And then this is just the structure on Chimera. So here's the enzyme bound inside of Januvia, and this is just more like more 3-dimensional looking at it. So under optimal conditions, developed through the test that we looked at in the table, the best pattern and collections of mutations starting with the ATA 117 enzyme. I'm sorry if you could hear that playing. I don't know if you can, but it's like,
Yeah.
really, okay. So the best, under optimal conditions, they were able to convert 200 grams per liter of this prostagliptin ketone to sitagliptin using the enzyme in 50% water, 50% DMSO. And then additionally, the biocatalytic approach compared to the chemocatalytic had a 10 to 13% increase in overall yield, a 53% increase in productivity, and a 19% decrease in total waste. So it was really effective in green reaction. And so the 200 grams per liter was really good, or pretty good for industry compared to something that was like 2 grams per liter, because you're able to make a lot more of your desired product in the same volume. So this was like pretty effective when it's implied in industry.
Great.
And
Does anybody have any questions? Biocatalysis.
So Scott, when you were talking about the table, you mentioned like, I know it was a combination of multiple people, but do you have any idea of the timeline it would have taken to do all of this? Because they're not showing like the ones that didn't work.
Right.
You know?
Yeah. People generally don't describe stuff that doesn't
Yeah.
work. You mean like how long it took to do this?
Yeah, how long did it take, do you think it would take to figure this out? Because obviously they had to have failures in between that aren't shown.
Yeah. That's a good question. So I don't know. Not exactly. But if I had to guess, because what they really have to do too is they have to like take the gene of the transaminase, this ATA117, the gene that encodes for the enzyme, and then they just need to start making mutations in the DNA sequence, which would then ripple through to an amino acid substitution when it's translated into a protein. They had to pick what positions, which I think they did based on some structural information. And then just even making the mutations is, people can do that pretty fast. That's actually not that hard. But then you need to make each protein and test it, right? Which some of those steps you might be able to do robotically. Some of the steps you would have to do by hand. I guess I have no idea, but I think if it was, now the other thing too is like this was done by Merck and another company that specializes in like enzyme evolution, meaning like changing the function of a protein to do something new based on what it used to do. So they're like really pros at this, like really, really pros. But even so, I would guess this took a collection of people years to do. Yeah. Yeah. But like Emily said, once they're done, now they have a gene that encodes for a protein. They can make as much protein as they want whenever they want. And that protein does a reaction in an extremely efficient, extremely enantioselective fashion at room temperature with mostly water as a solvent. So I think, from Merck's perspective, they're paying these people salary for a couple of years, and what they got at the end was a way to make however many tons of Januvia they make in a year. They're saving money every time they make it. You know what I mean?
Yeah.
Yeah. And then for us, it's just cool, right? Because we get to just look at the science. Yeah. But this process of like evolving enzymes to have new properties is, well, for biocatalysis, it's changing its catalytic properties, but this is something people have been doing for a while, and people are just getting like better and better and better at it because it's so useful. So. Any other questions for Emily? Nice. All right.